Okay, so we'll get started from where we left off last time. We were talking about complex power, and I went. When I assigned the homework, I assigned the use of some software tool. It's just a small educational tool. So here's a snapshot of what I expect what I expect from you to do. It's just simple snapshots and just discuss. So in this case, what do we have? Reactive power, active power. I mean, is it resistive load, reactive load, L, C? Huh?
Reactive. Yeah.
Why is
Resistive.
It's a resistive load, right? Remember when we said here the voltage and current are in phase. This is the voltage that we have in the system. This is the current we have in the system. Okay, maybe maybe there's some small phase angle. 1 watt negative power, sorry. Because you adjust it, you can play with the numbers, and maybe I didn't adjust it properly. But this is pretty much resistive, right? So you ignore the negative 1 watt here. Then the current will be in phase with the voltage, and negative watt should be 0. So sorry, I should have made it purely resistive here. So how about here? Yeah, the current is lagging the voltage. So this is the voltage zero crossing point. This is the current zero crossing point. The current is lagging the voltage, right? So we expect it to be inductive. So we will have some reactive power, and it's clear that we have some negative area under the curve, the instantaneous power curve, right? And the same thing with this case. Here, current zero crossing is somewhere here. It's leading the voltage zero crossing, right? It's leading the voltage zero crossing. You will also get negative an area under the curve, right? So anytime you have an area under the curve, it's not contributing to average power or real power transfer. It's contributing to reactive power transfer. This reactive power can be inductive or capacitive reactive power. Okay? Again, it's like the analogy for the bicycle, right? So where the bicycle, where you have 5-6 guys, this bicycle with multiple chairs. Everyone, if they're all sitting up straight and cycling, they're all contributing to real power transfer and moving forward. If one moves to the side, right, the person is still cycling, but some of his energy is used for balancing him to go to one side, and then another person has to balance that out and go to the other side as well, so that the bicycle doesn't fall down. Right? So one is adding negative reactive power, one is adding positive reactive power. Right? So, but at the end of the day, that negative or positive reactive power, what did it do? It reduced his ability to cycle and contribute to real power transfer forward. Right? Because some of his energy and concentration was placed on moving to the side. So same thing here, right? So we have a less amount of area and in the less positive area. So the positive area here is 188 watt. I mean, it's less. It was reduced by a certain negative area, right? So this negative area is what contributed to reactive power transfer. Do we need it? Yes, we need it. Right? That's what we talked about last time. You have to have reactive power. Anytime you have flux in any physical device, the circuit representation of that is an inductor, right? And an inductor means that you have inductive or lagging current, which means you have reactive power in the system. It's there. Anytime you have a generator, it's there. Motor, it's there. Cable, it's there. Anything pretty much has some inductance to it. Fine. Power electronics based fluorescent lighting. You can make that unity power factor. There's a lot of work you can do on the power electronics side to improve this, and you can add capacitors to the system where you have a lot of inductors in the system. You can compensate the negative reactive power with some positive reactive power, right? So you can do things like that. I mean, and Kahrama as a utility requires big industrial facilities to do things like that to improve the power factor. Ideally, we would like the power factor to be unity, right? So the angle between the voltage and current to be 0, but it cannot happen yet. Okay, so we realize now that the instantaneous power that is being drawn from the generator has several components: active power and reactive power, right? The book goes through the mathematical manipulation to prove that, from the instantaneous power curve, I can come up with two terms that are basically active power and reactive power. We did this graphically, but you can go through the derivation in the text. I don't have as long as you understand the physical phenomena from the drawing, from the graphics, I think that's what matters, to me at least. Yeah. So that we divided up the instantaneous power into active and reactive power, and we called the total power that's being transferred now from the generator apparent or complex power, and we discussed that last time. We discussed complex power in a single phase system. So we saw that we can represent that using a magnitude and an angle, which is v times I conjugate, so magnitude and an angle, so polar coordinates, or we can represent complex power using rectangular coordinates, and we can draw what we call a power triangle on the real and imaginary or complex plane, right? So we went through that, and so we just want to go and just apply a few more, do some more expansions based on what we know, with Ohm's law. Basically, you just reiterate Ohm's law as a definition and look at how it is represented, or how we would use it within the context of complex power. So we know that V equals the impedance times the current. So from the complex power equation, V times I conjugate, we will just substitute with Ohm's law in here and rewrite complex power in terms of impedances. So we just rewrote complex power in terms of impedances here, and we see that complex power is divided into the real power and apparent power, or reactive power. And the real power is nothing but the resistive component of the power, right? The I squared R component of the power, and then the reactive power is nothing but the I squared X component. So I squared times, XL minus XC basically is this X that I have here. So this is real power here, this is reactive power here, and just rewrite Ohm's law again, and you can rewrite this equation if you instead of writing V equals impedance times I, you just solve for I and then substitute. Instead of solving for V up here, we solve for I down here and rewrite the apparent power equation again in terms of voltages and impedances instead of currents and impedances, right? So sometimes you're given this, sometimes you're given that, and it's direct substitution. It's really nothing more than direct substitution, right? So, any questions on these equations? It's Ohm's law with direct and simple direct substitutions into the apparent power equation. Okay? And again, if the reactive component or the inductive component of reactive power will be I squared XL, right? And then the capacitive component will be I squared XC, right? That's this I squared times X here. Yes?
I don't understand why we use the conjugate.
Why we use the conjugate? It's a good question. I think we discussed that a little bit last time. So why they use it, honestly, I cannot tell you 100%, but what it does is complicates things. I mean, makes things not clear for us. So we talked about lagging and leading power factor last time, right? So we said that if V is here, I is here, right? So this is lagging power factor. But because of the use of the conjugate, right? When we draw the power triangle, we drew the power triangle this way, where S was here, and this was the same power factor, and this was the reactive power in the system. So I don't know why we use the conjugate, but what it does is sort of confuse you when you draw the power triangle a little bit. Okay, so I think it's because the standard is that we have inductive reactive power in the system, right? So when we wanted to draw the power triangle, I guess they wanted to represent it in this fashion instead of drawing a power triangle down here. I mean, honestly, I don't know why they use the conjugate, but what it does is confuse you a little bit when you draw this lagging power factor versus the power triangle. So this means lagging, and then this means leading power factor. Versus when you draw the voltage and current, this is lagging, and this is leading.
we don't do the conjugate, the answer is still correct.
No, because again we agreed. I mean, the power guys agreed on a notation, right? They agreed that this is the notation that we would use here. So they agreed that a load, for example, consumes reactive power. Consume is always positive. Remember in 214 you had the passive sign configuration where you had an element and current was going into the positive terminal, out of the negative terminal, and Dr. Hazim, I guess, maybe at that point, or Dr. Bina was saying that if an element has a voltage polarity in this fashion and current is going into the positive terminal, out of the negative terminal, then this element is absorbing, this is I, this is V, and then this element is absorbing power, right? So, and hence if this element is inductance, this inductance is sort of absorbing reactive power. So, and this is typically what we have in a power system: inductive elements absorbing or consuming reactive power produced by the generator. So we decided to call the QL a positive, give QL a positive sign, where QC capacitors are actually generating. Remember that the analogy for the guy is on the bicycle. One is absorbing the reactive power. He fell down on one side, absorbing the reactive power. You actually had to counter that physically, intentionally, by adding capacitors in the system to counter that and provide some reactive power. So in that case, the capacitor is doing what? Generating the reactive power. So according to the passive sign configuration from 214, an element that is generating power, instead of current coming into it, into the positive terminal, current's coming out of the positive terminal in that case, right? And in that case, remember the passive sign configuration, in that case Dr. Hazim or Dr. Bina was saying that in this case the element's power is negative. Remember, you used to put a negative sign and then multiply by the voltage and the current together, right? So it's because it's the opposite of the passive sign configuration. Does it explain? But also what it does is, confuse us a little bit on this lagging versus the voltage and current. We draw a lagging this way, but we will have to draw the corresponding power triangle as on the top. S will be at the top, and the theta will be to the positive instead of theta being negative, right? So I didn't come up with this, but I'm trying to explain it to you. Okay. So basically application of Ohm's law. Everybody's okay with this? Okay. And again, QL is always positive and QC will be negative, right? So this will be I squared QL minus, this is basically QL minus, Q is equal to QL minus QC. Or I squared XL minus XC as a magnitude. Again, we said it's always desirable to have non-zero reactive power, which means we would like to have unity power factor as much as possible. Not possible realistically because we have inductors in the system. Yeah. The other thing is, okay, so you can say, okay, why don't we just add capacitors enough to maintain unity power factor all the time, right? But loads change all the time, right? So factory turns, you turn on big machines, you turn off big machines, turn on big machines, turn off big machines, right? So and the load on the transformer changes throughout the day, right? We said the load curve changes throughout the day, so the load in the transformer will change, which means the reactive power required will change throughout the day. So if people like, so one way to install capacitors would be fixed capacitors. So the utility would, for example, install fixed capacitors in the substation, the transformer substation. They would install some fixed capacitors, some fixed capacitors, right? But if you install enough fixed capacitors to make the power factor unity, and then these people turn off their loads, what happens? Then you will have actually leading power factor in the system, right? Which is okay. But when we study a little bit later, when we look at generators and how they operate, we will see that generators don't like to operate in leading power factor. It actually reduces their total output power that they can provide. We will look at that a little down the road. So we want to operate with a lagging power factor, but not too much lagging, because you're too much lagging, then you're basically generating too much reactive power, which is reducing also the generator's limit to generate real power, which is what they're charging you for. So you always want to operate lagging, but with a reasonably good power factor, so 0.9 or 0.85 or 0.95. You want to operate lagging. But because these loads are changing, you cannot install huge big capacitors all the time, right? So what people do, so RasGas, for example, they would have these capacitors on their because RasGas is dictated by Kahraman to maintain power factor at a certain level. So they have to add these capacitors. They add these capacitors, but if their load changes, they switch them in and out. They put capacitors, different values of capacitors. They have capacitor banks that they switch them in and out. That's one. It's a mechanical switch. The problem with that is what? If you have a capacitor and you plug it onto a line, apply voltage onto a capacitor, what happens to the current through the capacitor? Immediately, right? So capacitor current changes immediately. So it's a huge inrush current, right? So huge inrush current, so very large currents. Very large currents on a distribution network, they cause voltage drops. Right? Because again, distribution networks are not like transmission networks. Transmission network, we have big transmission cables, right? Big diameter, low resistance. Distribution networks, smaller diameters, so larger resistances. Larger resistances means if you pull a lot of current in a short period of time, significant voltage drops which can affect other equipment, right? So that's one problem. The other problem is, again, if you have an AC current and then you add a small inrush, so you have a sine wave and then nice peaky transient, a small peak in the transient, small peaky transient. That is going to cause harmonics, right? You have a nice sine wave, but because of the inrush current, the capacitor, as soon as you plug the capacitor, something like this happens, right? So you no longer have a nice sine wave anymore. These harmonics also affect equipment negatively, right? So but it's a way. That's one way to do it, is switch capacitors, and people deal with it. They find ways to mitigate the effect of the harmonics. They make sure that their system will not be affected. So, like a load flow or power flow study that we will learn about in class, basically, you will conduct a power flow study on an industrial system or a small power system. There is a study called, harmonic penetration study. One of the studies that a typical power system or a utility or an industrial facility would conduct is a harmonic integration study. So they would study the effect of harmonics in different areas of the power system. So if you have harmonics here, if you switch capacitors here, what will happen to the equipment here? What will happen to the equipment here? What will happen to the equipment here? Because remember, there's a phenomenon called resonance, right? If you remember in 214, you studied the phenomena called resonance, right? If you have current or voltage harmonics at a certain frequency that happens to be the resonant frequency for any of the equipment that you have in the system, then what can happen? Then this resonant current or resonant voltage can be super high voltage or super high current, right? So harmonic resonance is an issue that people in power systems deal with very seriously. They want to make sure, for example, that the generator's resonant frequency does not equal any of the harmonic frequencies that you're going to possibly inject into the system. So they perform a study like that. And if it is, they have to add proper filters. Right? So this is another study that people do. We will not study that in 459, but it's something to note here. And then the other solution is to add capacitors using power electronics. That's the best thing to do, but it's the most expensive. Right? We studied that a little bit in 438 last semester, and basically simple, nothing but you have a capacitor, and before this capacitor, for example, add a box. This box here needs to be able to control when the capacitor comes in and out of the system. So how would you do that? Let's say you add a thyristor. What's a device called a thyristor, for example? Back-to-back thyristors. These thyristors are like diodes. It's like having a diode in this way and a diode in this way. It means I can have positive and negative current. I have an AC current through this branch, but in a controlled fashion. So I can control when these thyristors turn on. So I need certain amount of reactive power. I will turn on the thyristors that way, and for a certain period of time. And then at the zero crossing, this turns off. And then I turn them on again for a certain period of time. If my load changes, the duration of keeping the capacitors in the system, I reduce that. Right? Because this is nothing but it's a controlled diode. It's like a wire that you control. Okay, I will connect. I will disconnect. I'll connect, disconnect, but without the problems of the disconnection that you have with mechanical devices. Because mechanical devices, if you have mechanical devices, remember, with reactive elements want current and voltage to be continuous. So anytime you have a mechanical device, you will have some arcing across it. And you can also add some ways to suppress arcs and stuff in power electronics that is neat, yeah. Nice, neat ways to do it, yeah. But this is a way to change reactive power continuously. I don't have fixed capacitors. This is a C, yes, but I don't have this C on. If I keep these devices on for all the time, then I have this C connected to the system. Then if I keep this, if I turn these devices on for half the period, then it's like having a smaller amount of capacitors, right? And you can also add an inductor if you want, inductive system as well if you want, yeah. So you can, if you want to, if for example you have, for some reason you're worried about capacitance increasing, the reactive power increasing too much in the system, you can also do it with inductors. And they have ways to do it with both a combination of inductance and capacitance, so you can control reactive power in the system in a certain way as well. So it's there are many ways to do this, yeah. Many ways to skin the cat. But power electronics is the best way, but it's the most expensive because you need, okay, with just a mechanical switch, it's just sitting there. But anytime you have electronics, what do you need to do? You have to have a small substation room, for example, and this room has to be maintained and air conditioned, and or if it's not air conditioned, climate controlled. You cannot bring dust inside. Very different from, okay, you have a circuit breaker, air circuit breaker. It's enclosed in a chamber. You leave it outside. I don't care. Electronics, you cannot do that, right? It has to have a control circuit. There will be measurement and sensor devices. It's more expensive, right? Okay, so as we discussed, we can control power factor by adding capacitors or inductors, right? So, and there are many ways to add them that we just discussed. Okay, so this is one example. Let's go through that. So we have a single phase source. Okay, so we have a single phase source delivering 100 kilowatts to a load operating at a power factor of 0.8 lagging. Okay, so the first thing you do is start drawing. I read the first sentence. The first sentence I read was, I have a 100 kilowatt source delivering power at 0.8 power factor lagging. What do I know from this first sentence? I know I can draw P. Let me draw this nicely. So this I draw P here. This is my power triangle, right? This is my real complex plane, my power triangle. I can draw P equals 100 kilowatts. And it's a 0.8 power factor lagging, right? So where can I draw S? On top or on the bottom? On top. So it's 0.8 power factor, so power factor is equal to 0.8. So how do I find the angle theta, power factor angle? So cosine theta, or cosine phi, whatever you want to call it, is equal to 0.8, right? This is the power factor. So you inverse cosine 0.8, what is that? Okay. So we know that at some angle here, 36 point whatever, some angle here, theta, which is the inverse of 0.8, we can draw, I didn't draw it nicely, actually. Too high. Okay. This is theta, right? What else can I draw? I know this is the line I know for sure, right? What else can I draw? Sure, I can also find Q. Q what in this case? Due to inductive. So I call this QL. Q on top, I will call QL. Q on the bottom, I will call QC. Right? So, or Q to the pointing to the top, I will call QL. Q pointing to the bottom, I will call QC. Right? And then we'll see what they're asking for. So basically, I know QL, and I know from the power factor, and I know P. What else do I know? I also know S. Right? So I know S because I have theta and P, I can know Q and S, right? So cosine theta is equal to what? Adjacent over hypotenuse to S, right? And then sine theta is equal to opposite over hypotenuse, right? So from here I can find S, and then I can substitute here, and know theta and S, I know Q, right? So I know everything about the power triangle, right? So this is only from the first sentence, right? So I know what I have. Now see what else they're asking for. Calculate the reactive power to be delivered by a capacitor connected in parallel with the load in order to raise the source power factor to 0.9 lagging. Okay. So what are they asking for? What? They want to change. So this is my original power factor. This is theta. What do I want theta prime to be? Cosine theta prime, I want it to be what? I want it to be 0.9, right? So now I can go through the same. I have, but did they tell you the load change, the real power of the load change? Did they tell you the load change at all? This is my load. It did not change. I took this load, I connected to the system. Now I want to improve the power factor. If I improve the power factor, what will that do? That will allow my generator to provide less reactive power, right? Because now some of the reactive power is being provided by the capacitor, right? So inductor needs, capacitor throws in. Inductor needs, capacitor throws in, right? So so it's like, again, like the analogy for the bicycles, right? So somebody went, somebody on the bicycle now leant on the other side, so that the bicycle doesn't fall down, right? So now I want to improve my power factor. So I can draw a line here. Is it obviously this angle will be smaller? What's inverse cosine 0.9? 18.19. So it's almost half of this, right? Almost half of the original angle. So I can draw my theta prime line here. This is my theta prime line over here. My load didn't change, so my real power did not change, right? Did my load change? No, QL is the same, right? So QL did not change. So what did you do? We somehow we said that this was my original S. Now this is my S prime here, right? This blue from this point and this until this point. This is my new S prime, which means this is my new what? This is my new Q, right? How did I come to this? What was the result of this? For me to have to get this result, I have to add my old QL, which is the load that exists, and then what do? I have to add some negative Q to it, or QC to the QL that existed. So I added some QC here, right? So I think the question will be what? How much C did you have to add? Probably, right? We expect that to be the question. We did not continue until the end, but we expect that to be the question, right? So let's see what they say. So calculate the reactive power. They just asked for what is the reactive power. So calculate the reactive power to be delivered by a capacitor connected in parallel with the load in order to raise the source power factor to 0.95, not 0.9, sorry. But anyway, it doesn't matter. It's we did 0.9, but they asked for 0.95. So basically they're asking for this value of QC that they're asking for this value of QC that we had to add to bring this point down to a certain level here where this theta prime is 0.95, not 0.9. Okay? So how do you do the calculation? So again, let's see what else they ask for. Also draw the power triangle for the source and the load. Assume that the source voltage is constant and neglect the line impedance between the source and the load. So we did not consider an impedance between the source and the load. We just drew as if the load is directly connected to the source, right? We just drew the power triangle. Yes.
Why did we assume that the reactive power is constant?
Why did we assume? Because the load is fixed. The load did not change. You have a load here that is fed by this generator. This load is fixed. It will not change. Its active and reactive power consumption do not change. It's a motor, for example. For a motor to produce torque, certain value of torque, you need a certain, you remember, Dr. Haitham, at a certain speed, for you to control an induction motor, you were maintaining V over F constant, right? People that took 338? How many people took 338? 338? So induction motor control. Dr. Haitham was talking about the V over F control for induction motor, right? Why V over F? If you remember, what V over F constant means that the flux in the air gap is constant. So if the flux in the air gap is constant, then you will be able to produce a certain value of torque, a controlled value of torque that is between the minimum torque and the breakdown torque of the machine. Right? So, and this, if the flux is constant, then the reactive power is constant. Right? I mean, basically, we said that flux is basically an indication of reactive power, right? Or flux is resembled as a circuit element as an inductor, which means we have reactive power. So reactive power will not change. The load did not change. Your motor is supplying the same load. It's requiring the same amount of reactive power to link the stator and the rotor. The transformer is the same. It's supplying the same load, requiring the same amount of reactive power. So we have our source here and our load here that do not change. They do not change. This load dictates that we have current here. This current, if we have a certain voltage across the load, will not change, right? And this current now is being fed by the generator. But if I add an element here, which happens to be a capacitor, then this current is the same, right? And if I'm maintaining the voltage here, then it's the same, right? There's no voltage drop across this line. Right, so the voltage is the same. In this case, they said assume neglect source impedance, or neglect the impedance between the source and the load. Right, so the voltage is the same, the load is the same, so the current is the same. So the load is seeing the same things, same voltage, same current, same phase angle, same everything. Right, but because you added some element here, then the generator now will see something different. The generator now has to provide a different value of current, right? So what's going to happen is the capacitor will provide some reactive power to the load. So instead of now the generator providing all the reactive power that the load required, which was the original QL, now the capacitor is providing some QC, and the original load required some QL. So for you to know what the resultant power that is being delivered by the generator, you add this QL to the capacitor generated QC, right? And the new resultant reactive power produced by the generator, this is Q generator, right? This is what's going to be produced by the generator and delivered to the circuit. But the active power does not change because I did not add resistors in series. If I added some resistors in series, a different story, right? But the only real power consuming component is in the load here. It does not change. Okay? So any questions on this? Do you understand this? If you understand this, then the math is you go back to the previous slide. The equations for the math are very straightforward. But you have to understand this, the phasor diagram, QL, QC, this is lagging, this is leading, how do you calculate P and S from theta, etc., etc. Okay. Assume that the source voltage is constant and neglect that the line impedance between the source and the load. Okay. The solution is, of course, we know that the real power QS, the real power P is delivered by the generator, and consumed by some resistor in the load. So PS is the P source, and PR is P resistor, right? So the source is delivering power, real power component, to the resistor that's in the load that we have. Is delivered by the source and absorbed by the load, and is not changed when the capacitor is connected in parallel with the load, as the capacitor delivers only reactive power QC. Right? So the ideal capacitor is only going to deliver reactive power. It does not have a resistive element in it that burns power. Yeah. For the load power factor angle, reactive power absorbed, and apparent power, we can calculate those as follows. Right? We calculated the power factor angle from the original power factor angle from the inverse cosine of the power factor. So originally the power factor was 0.8, inverse cosine of that was 36.87, right? So we were able to draw the line or the trajectory for the S, for the apparent power. And because we have P, which was the real power component, we were able to draw Q because it's perpendicular to P until it intersected with our trajectory for S. So we were able to do that. And you can do that same thing with the math from the trigonometry that we went through before as well, right? So Q in that case, the original Q, QL, was calculated as 75 kilovars, right? So the units for real power are watts. Our units for reactive power are VARs, volt ampere reactive. The unit for complex power is volt amperes, VA. Okay? Any piece of AC equipment is rated in volt amperes. You could not go and tell somebody, I want to buy a 100 kilowatt transformer. They will look at you up and down. Right? You cannot do that. You can tell them, I want a 100 MVA transformer, 100 kVA transformer, right? Because it depends on power factor. The rate, again, we know that a certain amount of power can be transmitted or processed by this transformer. Whether you are operating with a leading or lagging power factor, the transformer vendor does not know, right? The transformer vendor is none of his business, right? Your business is to control your power factor. So he will tell you, my transformer can process 100 volt amperes. Now you have the luxury. If your power factor is close to unity, then you're utilizing your transformer pretty well. If you have a very poor power factor, then you're not going to be able to deliver much real power through this transformer because all of it is reactive power, for example, right? So when you go and buy AC equipment, motors, transformers, generators, all of these are rated in volt amperes, okay? MVAs, megavolt amperes, kilovolt amperes, volt amperes, all AC equipment is rated in volt amperes. Okay, so we were able to calculate Q and we were able to calculate S from the given information. And that's what we did initially when we drew our original red triangle, right? We were given P, we were given theta, drew the trajectory for S. After drawing the trajectory for S, we can connect these two lines here. This is perpendicular, so we have from triangular trigonometry, we were able to, given theta and given P, 100 kilowatt, we were able to calculate P and Q, S and Q, right? From sine and cosine or tangent or whatever you want, right? So everybody's okay with that, right? So then, okay. Then they gave us the new objective for power factor. The new objective was to operate with a power factor of 0.95. So we had to calculate a new power factor angle, so a new trajectory for our apparent power. So the angle in that case was inverse cosine 0.95, which was 18 degrees. So same thing, we can calculate the new S and we can calculate the new Q, right? Same thing as like we did before. So we can calculate the new Q and we can calculate the new S. Right, same process that we did before, just triangular geometry from the triangle, yeah. And then if you know your new Q, right, your new Q is this QS after you improve the power factor. Then we said that given your new Q, which is this one, this Q is equal to what? QL plus QC. So the Q provided by the supply or the generator now is equal to QL plus QC. QC is a negative number. We know that, right? So it's in the opposite direction of QL, right? These are complex numbers, so you have to pay attention to the direction here. So this is S. So QC then is the difference between the old QL as a magnitude and the new QS as a magnitude, right? So we took my original QL, I have the new QS, which is supplied by the generator. The difference between them is the capacitive reactive power, right? So any questions on this? Yes?
Is it possible to have a lower power factor?
Lower? What do you mean lower? Yeah, you can. 0.99?
No, I mean it was 0.8.
Yeah. Ah, yes, yes.
0.7.
Yeah. You go to your home, it's going to be probably 0.7. Because the air conditioners, you know, these split unit air conditioners, they're horrible. They have very poor power factor, actually. Especially the old ones. I mean, the new ones, maybe they're better regulations now, but yes, very poor, very poor. Very poor. Fluorescent lighting, unless it's very expensive kind, where you have, because it's power electronics based, but not necessarily power factor corrected. So with power electronics, you can do anything to the voltage and current, right? So with fluorescent lighting has a poor power factor.
Then QL will be.
Computers.
We will add more QL, right?
In that case, you will be adding more QL. So you will require more QC to bring you back to the 0.95 power factor. Right? You have a larger QL, so you need more QC to maintain power factor at a certain angle. No, our homes are the fridge. Fridge is nothing but a simple induction motor, right? So poor power factor. These single-phase induction motors, power factors are very poor, 0.7, 0.6. Not very efficient from a power transfer perspective, I would say. But I mean, this is what we have. But again, consumers, we're nothing. I mean, home consumers are not really what's consuming reactive power in the system. What's consuming reactive power in the system is all the factors, all the big motors and machines that we have in Ras Laffan, in Misaid, in Dukhan. I mean, this is what's consuming reactive power, and that's why the utility forces them to regulate the power factor. For us, the utility can put small capacitors in the substations close to our neighborhoods, and that will take care of maintaining the power factor at a reasonable value. Yes?
Do we have variable capacitors in the market?
But that's the power electronics based. No, as a physical thing, the capacitor itself varying, I don't think so. You will add, typically what we do is you have a fixed capacitor and you add power electronics to connect it intermittently to the power system here. And that is called, the technical term for that is called static VAR compensator. Right? Static refers to power electronics, basically. It's called SVC, static VAR. VAR is volt ampere reactance, right? It's compensating the VAR in the system. Static VAR compensator. So I don't think we have any installed in Qatar. My cousin works for Siemens in the UAE, and he's working on a project where they're installing a system like that. And Qatar's power system is small, very dense. So the utility I think it's easier for the utility to be able to control power factor by adding some local substations. We don't have very long distances either, so it's different. You may not need something like that. So, any questions on this example? So, what's the next thing that I can ask on this example? Exactly. What the value of the capacitor I can add. So, you have QC is equal to 42.13. You can go back to your equations that we have here. So, QC is equal to V squared over XC, or V squared times omega C. So, if you know your frequency and you know your voltage level, right, then you can calculate the capacitance in that case, right? Really, that's it. There's not much more. It's not complex, but I mean the idea that this physical phenomena is something you need to understand well. The power triangle you need to understand well. The relationship between this and leading and lagging power factor is what you need to understand well. If you go to an interview, they will ask you about this. They will ask you about lagging power factor, leading power factor. How do you improve power factor? They will ask you about this. This is what power engineers do. And then you can also do this with PowerWorld. So you can confirm your answer yourself, right? You don't need to have a solution manual. You can simulate the system. So you have a generator here connected to a bus bar, connect a load here to another bus bar, connect them with a transmission line, and you can add a capacitor in parallel. And you can start playing with the amount of kilovars that you need to push real or reactive power. So I believe the green and the blue indicate here real and reactive power. Okay. So here in this case, we had a considerable amount of real and reactive power. We had 0 kilovars supplied by the capacitor. If you increase the kilovars provided the capacitor, I think the blue is the reactive power. So then you will find one of these arrows, the size of these arrows going down. Right? Power World will let you do that. Yeah. Okay. We talked about balanced three-phase. I think the last class. This is just a quick review of that. So again, balanced three-phase is where we're providing our loads, or when our generators are providing three voltages that are 120 degrees out of phase, and they are equal to each other, right? And if you flip, so if you're standing here, these are phasors, right? These are time domain signals that are changing with time at a frequency of, in here, for example, 50 hertz, right? But in the phasor domain, we represent them as a magnitude and an angle, right? Remember the relationship between time domain and phasor domain. If you stand here and rotate the system, you will find VA first, and then VB, and then VC, right? For a person standing here, and with this system rotating, you're standing here and the time domain signals are passing by, you'll first see VA, then you'll see VB, and then you'll see VC. And we call that positive sequence, right? Why do we call it positive sequence? Because we also have negative sequence, right? So negative sequence is if you stand here and you see VA, and then you see VC pass by, and then you see VB pass by. This has some significance, right? In 338, you study that if you flip the terminals of the electrical supply to a motor, you will flip its direction, right? So we will see later in a power system, when we study chapter, I think, 9 or 8 or 7, we will see that a power system has a mix. So even though we measure here, we find VA first, then VB, and then VC, then anytime your power system sine waves, your voltages are not pure, or currents are not pure sine waves, then, and they're not equal to each other exactly, then you also have, in addition to some positive sequence, the majority of positive sequence that you have in the system, you also have some negative sequence in there. And we come up with a mathematical tool to help us. Okay, if I have this waveform, so if I have a three-phase system where this is VA, this is VB, and VC. This is VA, VB, and VC. If you just look at it this way, you think that this is a positive sequence system, right? This is positive sequence. You're supplying your load with a positive sequence. My generators are generating VA, then VB, then VC. If I measure the signals, all the three phases together, I will see VA, then VC, and VB, then VC, right? But what you notice here is, and assuming these are 120 degrees apart, so these are 120 degrees apart. But if the magnitudes are not exactly equal, then you have some unbalance, right? If the magnitudes are not exactly equal, that you have some unbalance. The way we will represent that is, and then okay, if we have some unbalance, does that allow us to? You remember when we were talking about three-phase, single phase, and three-phase? You know, our three-phase loads here, our three-phase sources here. When we started supplying the loads initially with single phase, and then we said we want to reduce the number of cables, and we did that by, okay, we join all of these together, and we said, all right, we join all of these together, and the sum of the current in this node is what's coming out if we make this one single cable, right? And then we said that, fine, all of this current will come here. This is current supplied by this source to this load, current supplied by this source to this load, current supplied by this source to this load, so we have a three-phase system. But then we said, okay, we want to using 6 wires originally, and then we said, okay, let's join all of these together. If we join all of these together and bring one single cable back, join all these together and bring one single cable back to the source, to the three-phase sources. This won't affect anything. If this is I will have 3I here. This is I will have 3 times I flowing back here, right? But if I phase shift these sources with respect to each other by 120 degrees, I will still be able to supply my loads, right? So what? The loads don't care about the phase of the voltage. Unless they are sensitive, there are certain loads that will care about the phase of the voltage, okay? But assuming that these loads don't care about the phase angle of the voltage, right? If they don't care about the phase angle, lights, for example, I don't care. They will light up. Right? Do they care? I don't think so. Ask Siri. So I really, I don't think they care, right? So Since they don't care, what we said, okay, let's do this. Let's phase shift them by 120 degrees. You phase shift them by 120 degrees, then the sum of the currents here will also be phase shifted by 120 degrees, because this is 0, 120, 240. And then when you add 3 phasors that are 120 degree apart and equal in magnitude, the sum will be 0. So we said that the neutral current will typically be 0, and in transmission systems we typically remove that neutral current, the neutral cable. In distribution systems we will leave it. So, but if the voltages are not perfectly balanced, this does not exist. The voltage is not perfectly balanced, we will have some neutral current. And these 3 will not sum up to 0. So in that case, we will use a mathematical tool in chapter 7 that is called symmetrical components. It will allow us to take these 3 waveforms and chop them up into a positive sequence that is balanced, a negative sequence that is balanced, and also something called the 0 sequence. Why do we want to do that? And when we didn't have to use the neutral line, what did we say? We said that I can take this circuit and solve it by itself outside. Because I can connect this point to this point. This point is connected to this point, and I can solve this circuit independently. I can have a single phase equivalent circuit. That's what Dr. Haytham was using in 338 as well, right? He was using that because everything was assumed balanced. Because everything was assumed balanced, then you can take one phase of your load and one phase of your source, hook them together and solve. Right? Anytime you have an unbalance, you cannot do that. Right? So we only know how to solve simple circuits. We don't like to solve complicated circuits. I do first order differential equations, not second order, right? So I know Mariam is very good at math and stuff, but for me, really first order is my maximum. Yeah. So what we do is, we'll find a way to chop up our unbalanced system into a positive sequence that is balanced, negative sequence that is balanced, and a 0 sequence that has equal magnitudes, and we will talk more about it later. Yeah. But for now, let's talk about positive and negative. Yeah. This negative sequence is also doing what? If you have both positive sequence and negative sequence in your supply, it's like having the motor spin in one direction and also having it spin in the other direction. So what is that doing? That is adding current into the motor that is not providing extra torque. That is actually providing opposing torque. Right? You want to spin it in one direction and you want to spin it in the other direction. So the sum will be the winner, the difference between them, right? So you will be putting in current from positive sequence, current from negative sequence, but the torque will be less. So you're just burning power in the motor. So motors that are fed by unbalanced supplies will get hot. Transformers that are fed by unbalanced supplies will get hot, right? So it's something so you will have to protect against that. So there will be a protection relay that we will maybe look at the end of the semester that measures that. It measures the fact that there is an unbalance. And then if there is an unbalance exceeding a certain amount, it will turn off the system. Turn off the machine because it doesn't want to burn it yet. Okay. So any questions on this? Positive, negative sequence? But the main goal here is the beauty of being able to do single-phase equivalent circuits. Okay. So anytime we have a balanced system, whether it's positive sequence or negative sequence, any balanced system, 3-phase balanced system with 120 degrees apart voltages and currents, then we can do single-phase equivalent circuits. I would like to do that because I don't want to play with 3-phase systems. If I have to play with a 3-phase system, I will connect the 3-phase voltage sources here, solve too many loop equations, have too many unknowns, and I don't like that. Not because I don't like that, it's because our power systems have tens of thousands of nodes. So take these tens of thousands and multiply them by 3, right? And actually, when we solve power systems, we're also solving for many quantities, real power, reactive power. So we will typically have 2 equations at every node. We want to know the active power and reactive power at every node. It's very important for us to know active power. 4 variables we will want to know all the time. Active power at a node, reactive power at a node, voltage, magnitude, and angle. These are the 4 variables we want to know. And for these 4 variables, we'll always have 2 given, and we want to always find 2. Right? So at every node, we're going to have at least this set of equations. So can you imagine multiplying those by 3? Right? It's a lot of equations. So we want to, there's a lot of power system research on how to reduce matrices and simplify equations and approximate and all of this kind of business. Yeah. So to allow us to solve a power system very quickly, as fast as possible. Yeah. So single phase equivalent is a must, and it's very easy to use. It will help you do your you can do your homework in 3 phase if you want, but it will take forever. Yeah. So we will figure out a way now to take all our loads that we have in a system, in a 3 phase system, and convert them to single phase equivalent. That will be the objective, right? So everything we have in a power system, transmission lines, transformers, generators, loads, everything we have, we want to take in as a take the three phase representation and figure out how we can represent it as single phase, right? Everything in a power system is either connected in a star fashion or a delta fashion. So it's gonna be either connected in star like we so this is a star connected source and this is a star connected load, right? So remember, we can, from our discussion, we can connect these 2 points. If we connect these 2 points and we know that there's no current flowing, I can basically take this node here and this node here and bring them on top of each other. If I bring them on top of each other, it's like I'm solving only this circuit by itself, right? These 2 nodes are right on top of each other. There's no current flowing here, there's no voltage drop. So if you do a loop equation, it's just a single loop with one source and one load. That is the beauty of the single phase equivalent balanced circuit, right? So with a star connected system, it's easy. If it's a balanced system, I will, take one phase of my source and one phase of my load. Solve my circuit, and here I can add a transmission line, for example, impedance as well, right? I can add a source impedance for the generator. I can add a capacitor as well, like we just did in the previous example. I can add anything I want, right? But because, okay, a capacitor here, I added it, it means I have to add also one on this phase and also one on this phase. In this case, it's a 3-phase balanced load. So since it's a 3-phase balanced load, all I need to do is take a single phase equivalent. So my single phase equivalent is very simple. Here I can add the generator impedance, I can add the line impedance, but they're all identical circuits. And my sources are balanced and my loads are balanced. So I can take a single phase equivalent circuit and solve, right? So with a star connected system, it's very simple. But you have to be careful that the voltage provided here is called what? This is the phase voltage provided by my source, right? Is this voltage equal to this voltage? It's not. If this is VA, this is VB, this is VA, this is VB, what is this voltage? VAB is equal to VA minus VB, right? So this is called the line voltage in this case, and this is called the phase voltage. So there's a difference in magnitude, and then there's a difference in phase shift. We will look at it on the slide as well. So when you solve your single phase equivalent circuit, you have to make sure you pay attention to the fact that, typically in the problem you will be given line voltages RMS. This is when we talk. Okay, the system, you have a 3-phase load supplied by a 100 kV generator, right? This will be a 3-phase 100 kV generator, and 100 kV will be the line-to-line RMS voltage. So if you're going to go and solve your single phase equivalent circuit, you have to make sure you pay attention to the fact that there is a difference between the phase voltage and the line voltage. So you have to keep that in mind. And that's the differences and stuff will be shown on this slide. So if this is the phase voltage for a 3-phase load, so this is my VA of the load or the source. This is VA, phase voltage A, phase voltage B, phase voltage C. Then if I would like to know what the relationship between the line voltage VAB and the phase voltage VA, I know that VAB is VA minus VB. So I use phasor graphing techniques, and I basically take my VA here, I add it to a negative VB. So this is my negative VB. Bring this negative VB to the tip of VA, add them together. So this is my VAB. What do you notice about VAB? It's larger magnitude, and is it in phase with VA? it's leading VA by 30 degrees, and the math is here. So the trigonometry that is needed is over here. But if you do the math, if you look at the trigonometry, basically, yes, VAB is leading by 30 degrees, and it is square root of 3 larger than VA. Right? So the phase voltages are square root of 3 less and lagging the line voltage. Or the line voltage is square root of 3 more and leading the phase voltage. Right? So given the line voltage, which is what you will typically be given. You will typically be given the line voltage in a problem. You will have to convert that to phase voltage. So if you're given a line voltage, I don't know, 100 kilovolt angle 30 degrees. So to solve a single phase equivalent circuit, you will have to subtract 30 degrees from the angle and divide the magnitude by square root of 3. Okay? Everybody's okay with that? And for currents, it's easy. The line current is equal to the phase current. So for a star-connected load, line current is equal to the phase current. Right? So line and phase currents are equal. Line neutral voltages, which are the phase voltages, are we typically call them VAN. So VA with respect to the neutral, VB with respect to the neutral, and VC with respect to the neutral point. And the line voltages, we call them VAB, VBC, and VCA. Line voltage is given as voltage is typically given as a line-to-line voltage in problems. So you have to make sure that you pay attention to that. So voltages are typically given as line-to-line. So if you want to know the phase voltage, you have to use this relationship. So the line voltage is equal to the phase voltage multiplied by square root of 3 and phase advance by 30 degrees. Okay, we will do an example, so it should not be a problem. So any questions on this? The other type of load that we have in a system is called the delta connected loads. This is a bit of an annoying thing to have in a system from our perspective. So we had our three-phase generator here that was star connected. And when we had our three-phase load that was star connected, life was easy. Right? Everything was balanced. If everything was balanced, I know that these 2 points I can connect. If I connect these 2 points, I can solve this single phase equivalent circuit, right? How about for my delta connected load? Delta connected load, I have an impedance here, impedance here, impedance here, this is connected here, and this is connected here. Now what? I don't have a neutral point, right? How about, okay, let's look at the relationships between the voltages and currents, right? So this was my phase voltage from my generator, right? And this was my line voltage from my generator. Now what is the phase voltage for my delta load? It's the same as the line voltage for the star connected generator, right? So it's a bit annoying now. I don't know what to do. So what's the solution? Yes? I was asking about the phase voltage of the delta connected load with respect to the line voltage of the source, right? They're the same. The phase voltage of the delta is equal to the line voltage of the source versus the phase voltage of my star connected balanced load was equal to the phase voltage of my source, right? So it's a bit confusing now, right? And I don't want this to happen because remember, what was the single phase equivalent circuit was nice because I was also only solving circuits in phase A using the voltage source in phase A, right? I was solving for currents in the loads on phase B using the voltage source on phase B. But now I have a relationship between phase AB voltage and current in phase A, for example. So I don't like that, right? So, but as power engineers, we found a way around it. So let's see what we did. First, let's talk about the relationships between the voltages and currents again, and then we'll see how we can solve that because I don't think we can. It's not easy to come up with a single phase equivalent circuit anymore, right? I have a system now with a nice connected star load, a nice connected star source, which I can solve as single phase equivalent. But then somebody put this delta connected system in the middle. It ruined everything. I don't have a neutral point. I cannot connect all the neutral points together and solve a single phase equivalent circuit. So we will have to find a way around it. Okay, so first let's learn about the delta, the voltages and currents in a delta versus the, and look at those relationships, and then we'll see what we can do about it. So in a delta connected load, the line currents are not equal to the phase currents anymore because there's a node here, right? So the line current IA is equal to the difference between IAB current and ICA current, right? So you have that relationship here. And it's not only the magnitude that's affected, it's also the phase that's affected, because we're talking about phasor quantities. IAB, IBC, and ICA are all 120 degrees apart as well. Why would we want that to happen actually? Why would we want the line currents in the delta to all be 120 degrees apart? Yeah, if the voltage is, because okay, this is, let's assume these are resistors. If we assume these are resistors inside here, and the currents here are all equal in magnitude, but they do not sum to zero. They're not 120 degrees apart, right? If this current is 1, this current is 1, this current is 1, right? It's one current. It's one current that is 1 magnitude 0, right? If the current is 1 magnitude 0, and these are 3 resistors, and these currents are all in the same direction, right? Then the voltage drop across this, plus the voltage drop across this, plus the voltage drop across this, is not going to equal 0. Equal some value. If they are not 120 degrees apart, right? If they are not 20 degrees apart, I want to do Kirchhoff voltage law around this loop. If these are DC sources, this current is in this direction, so the voltage is in the opposite direction, right? Voltage polarity will be the opposite of the current polarity. Voltage polarity will be the opposite of the current polarity. Voltage polarity is the opposite of the current polarity, right? Correct? No? Guys, come on. These are the 3 resistors. Currents are in the same direction. Right, it's here. Let's draw outside. Three resistors. Current is this direction in all 3 resistors. Right? This is I. So what is V across these 2 points? It's IR plus IR plus IR. Right? So it's 3IR, or 3R times I. Right? So it's a voltage that's developed across the combination. Right? But what if, magically, this current and this current and this current are 120 degrees apart? This is I but 120, this is I but 240. You will still add the 3 voltages, but these 3 voltages now will be 120 degrees apart. So if you add them up, the sum will be 0, right? And we don't want current to be circulating inside the delta. Let's say this is a motor or a transformer, right? If there is current circulating inside here and not, there is current circulating inside here continuously, then what's going to happen? I'm just heating up the phases. This current has no relationship with what's outside. There's no relationship. Is there any relationship with what's outside? This is additional current that is circulating inside the delta. Yes, no. If I look at the current here, current coming in, current coming out. There's no relationship. Sorry, here in this case there is. Sorry, and this, if there's I here, fine. It's the same I coming in, same I coming out. And current is moving in the phases, but it's moving in these phases, and it's adding. The voltages add up. They add up to something. If I have a voltage and I close a loop around it, what do I end up with? I end up with a current, right? If I have a voltage develop across the loop, if I have these three resistors, if I have the three resistors here and the currents are not 120 degrees apart, so it's not a balanced system, then what's going to happen? Or if this is a generator, forget about it being a load. Okay, if I have a generator, let's look at this. DC here, right? And then DC here, and then DC here. What's going to happen? Superposition, right? How do you solve for the current in the circuit? This is V1 plus V2 plus, this is V3. How would you solve for I? R, R, R. Come on, what's I equal to? Yeah, so V1 plus V2 plus V3 over 3R. What? Yeah, plus V3. So all the voltages divided by the resistance. There will be current circulating inside here, right? But if these voltages happen to be, if there is current circulating inside a machine, right? And this current is not really coming from outside. It's not coming from outside. Or this is a generator. And this generator happens to be generating DC instead of AC. You put three generators like that. Is current going to go to the load? No, because this current here is equal to this current here. Sum of current around this node is 0. This is I, then this, and this is I. So what is this current? This is I, this is I. This is 0. Right? So no current will come out of this generator. Right? But if this generator happens to be generating three-phase voltages that are 120 degrees apart, there will be no current circulating inside the delta. Current will be going outside to the load. Okay, we will talk more about that in the future, but is it at least a little bit clear? There will be current circulating. If these are not voltages that are 120 degrees apart, then there will be a total voltage. I mean, when you add them up, there will be some voltage existing, and you close the loop, there will be some current circulating inside the delta. That will not go to the loads. Connect the load, nothing will happen. And this will only heat up the system. So that was what I was trying to say. We will talk about this more maybe when we talk about protection. So anyway, so in a delta configuration, so line voltage and phase voltage are equal. So this is the line voltage, right, between the two lines. It's also equal to the phase voltage, correct? The line voltage and phase voltage are equal. Phase currents are what's flowing in the phases, of course, and then the line currents are what's coming into the line from through my line and distributed among the phases. So there is a relationship between the phase currents and line currents, and it's the same as, it's sort of opposite as what we had in the previous case. So here I had ICA, IAB, and IBC are my phase currents, right? So this is my phase current IAB, phase current IBC, phase current ICA. If I want to find my line current is the difference between these two, right? So IA plus ICA is IAB, right? I have my phase current IAB and IBC and ICA. So IA is equal to what? IAB minus ICA. This is IAB and this is ICA. I take the opposite of ICA and add it to the end of IAB. So I end up with my line current IA. So my line current in a delta, what is square root of 3 greater according to the math that we have here. So it's square root of 3 greater and lagging by 30 degrees. So opposite of what we had before for the star. For the star, I had my line voltage, square root of 3 greater, but leading my phase voltage by 30 degrees, right? In a delta, my line current IA is square root of 3 greater, but lagging the phase voltage by 30 degrees, okay? Why is all this important? Because as we said, we're going to find a way to solve all our circuits using single phase equivalent circuits. So if I'm going to solve use single phase equivalent circuits, then I have to know how to convert between phase and line, and vice versa, right? We also said that we don't know how to deal with the delta, right? So the power engineers came up with a nice way to deal with it, right? So this delta as you connect it, load. This is my star load, delta load, right? Connect to the generator. I can put a box around this, and I can put a box around this, right? And I can look at the voltages here, and I can look at the voltages here. And I can look at the current flowing into this box, current flowing into these terminals. So I can look at the voltages and I can look at the currents. And for a star, I know the relationships. I know the relationships very easily. I know how to take the star load and convert it to a delta. But if you go through, there's some math in the textbook that it's not going to be explained in the slides. But the idea behind the math is we find an equivalent delta star representation for the delta connected load. So I will deal with this as a black box that is consuming power. This power is at a certain voltage and a certain phase angle for the currents that are coming in and the voltage that are applied. And I will say, okay, an equivalent star representation for this delta will look like a star, but it will have a certain impedance. This impedance will be different. And that's what we have in the next slide. If we go through the math that's in the textbook, and I don't want you to derive it, right? But the objective is we found an equivalent star for any delta. The equivalent star for any delta will take the value of the impedance of the delta and divide it by 3 and draw it as a star connected load. If you do that, then I can take any delta connected load in my system, convert it to a star. If I can convert it to a star, then I can solve my single phase equivalent circuit. But then I have to remember, right? I converted it to a star, and all these relationships between the phase angles and magnitude, square root of 3 plus 30 minus 30, will confuse you. This is the only thing. This is the most difficult thing in this, I think, in the course. The square root of 3, is it greater than? Is it larger by square root of 3? Less than by square root of 3? Is it leading by 30 degrees or is it lagging by 30 degrees? If you get this well, I think it should be, you'll do pretty well here. So what we did is come up with this equivalent star, and now we can solve all our systems simply using a delta. So we'll go through the equations next time, and we'll go through an example. And we will see that I can take this large, small example of a power system and connect instead of having a star and a delta, convert everything to a single phase equivalent system where I only have stars. That's what we'll do next time.